Welcome to episode 55 of George's Random Astronomical Object. Every episode, I run a random number generator to select random astronomical coordinates in the sky, and I then search for an astronomical object near those coordinates and talk about what makes that object so interesting to astronomers. So let's now run the random number generator. And there's a burning marshmallow smell coming from the random number generator, which means that I have to unclog the creamer. The coordinates for this episode are 0 hours, 1 minute, 57.9 seconds for ascension, and negative 15 degrees, 27 minutes, 50 seconds declination. These coordinates point to a location in the constellation Cetus. If you've listened to some of my previous episodes, you may have heard me discuss how the ancient Greeks thought that the constellation Cetus looked like a whale or sea monster, even though it doesn't look like much of anything. This demonstrates that the ancient Greeks apparently used lots of mind-altering substances. Anyway, the specific object that the coordinates point to is the Wolf-Lundmark Galaxy, or WLM Galaxy. This galaxy has a rather weird name that belies the weird history of its discovery. The galaxy was originally identified in 1909 by Max Wolf, who was a German pioneer in astrophotography, but somehow his discovery was either forgotten or overlooked. Maybe because Wolf was busy publishing papers on just about anything that he photographed in the sky, and no one noticed that he had published the discovery of an entire new galaxy. In 1926, Philibert Melot and Knut Lundmark rediscovered the galaxy. Sometime after that, people figured out that the thing discovered by Wolf and the thing discovered by Melot and Lundmark were the same thing, so they started calling it the Wolf-Lundmark Galaxy. However, that would get tedious to write on mid-20th century typewriters, so they called it the WLM Galaxy for short. Interestingly, this object was discovered before Edwin Hubble and other astronomers had figured out that other galaxies are actually objects located outside our own galaxy, so the WLM Galaxy was originally referred to as a nebula. Anyway, this is a dwarf irregular galaxy, although it actually does not look that irregular. Most of the stars lie within a slightly distorted oval region that runs north to south as seen on the sky, and a few nebulae are scattered around one end of that oval. This oval region actually appears to be a bar-like structure in 3 dimensions. Radio wave observations of this galaxy show that this bar structure sits within a disk of gas that extends about 2.5 times as far from the center of the galaxy as the stars. One of the interesting things about the WLM Galaxy is its location. It lies within the Local Group, which is the gravitationally bound group of galaxies that includes the Milky Way, the Andromeda Galaxy, the spiral galaxy M33, and many other dwarf galaxies. Most of the Local Group's dwarf galaxies are either in orbit around or gravitationally interacting with either the Milky Way or Andromeda galaxies, and some of the dwarf galaxies are gravitationally interacting with each other as well. The WLM Galaxy, however, is located at a distance of 984 kiloparsecs from Earth at the edge of the Local Group, where it is relatively undisturbed by everything else that's going on. It's kind of like the quiet kid at the edge of the playground reading a book, while the other dwarf galaxies would be like the kids near the center of the playground shouting about wanting their turn on the swings or pushing other kids off the slide. And I suppose the Milky Way and the Andromeda Galaxy would be the parents trying to manage everything. Astronomers like to study the WLM Galaxy because it provides insights into what dwarf galaxies are like when they are left undisturbed. For example, gravitational interactions between galaxies can change the orbits of those galaxy stars and interstellar gas clouds, so the WLM Galaxy shows what the orbits of these stars and gas clouds looks like in an isolated dwarf galaxy. In fact, the WLM Galaxy's isolation is probably one of the reasons why it has such a big gas disk. If it was closer to the center of the local group, one of the other kids probably would have taken the WLM Galaxy's hat. Or actually, I mean one of the other dwarf galaxies, or even the Milky Way or the Andromeda Galaxy, might have gravitationally stripped away the WLM Galaxy's gas disk. Gravitational interactions between galaxies also tend to cause the interstellar gas clouds within the galaxies to collapse and form new stars, including very bright blue stars that have very short lifespans before they explode to supernovae. I suppose, using the playground analogy, this would be like kids accidentally colliding with each other on the playground and getting bruised, which would be like stars forming, maybe, and their kneecaps exploding as supernovae? Anyway, the WLM Galaxy is a really good place for astronomers to look if they want to understand how stars form, evolve, and die in the environment of an undisturbed dwarf galaxy. This is actually quite important because the elements heavier than hydrogen and helium that we find within interstellar gas clouds within our galaxy and other galaxies were initially created by fusion within the interiors of stars and ejected into space when the stars died. After this, when new stars form out of the gas in the interstellar medium, they will contain some of the heavier elements made by the older stars. For multiple reasons, the stars in interstellar gas and dwarf regular galaxies contain fewer of these heavy elements than the stars in interstellar gas and larger spiral galaxies. Astronomers are still trying to understand the details of why this happens, so they end up spending a lot of time studying the WLM Galaxy to observe how stars in undisturbed dwarf galaxies are forming these heavy elements. Even though the WLM Galaxy is located at the edge of the local group, it's still close enough that astronomers using modern telescopes can identify and study individual stars within the galaxy. This allows for all sorts of interesting scientific analyses. To begin with, astronomers can often measure very precise distances to nearby galaxies if they can identify specific types of stars within those galaxies. The idea is that if astronomers know exactly what type of stars they're looking at, then they know exactly how much total energy those stars are supposed to radiate, so they can measure how much of that energy reaches Earth to determine the distances to these stars. Because the WLM Galaxy is so close that astronomers can identify many different types of stars within it, the galaxy has actually become very useful for testing which specific stars can be used for measuring the most accurate distances to other galaxies. Also, as I mentioned before, the WLM Galaxy, like a lot of other dwarf galaxies, contains relatively few elements heavier than hydrogen or helium. Consequently, the WLM Galaxy is not only a good place for studying why dwarf galaxies have fewer heavy elements, but also for studying individual stars that contain relatively few heavy elements, and learning how they differ from the ones that we find in the Milky Way. So that is why astronomers spend so much time observing the WLM Galaxy, and the location on the Earth's surface corresponding to the position of the WLM Galaxy in the sky is about 2/3 of the distance from Angola to St. Helena in the Atlantic Ocean. St. Helena is one of the most isolated places to live on Earth, so the WLM Galaxy's association with it makes a lot of sense. If you're interested in listening to more podcast episodes associating astronomical objects with other people, places, and things, then you can go to the website for this podcast at www.randomastronomicalobject.com. You can visit the website to download episodes of the show, read information about the astronomical objects, view images of those astronomical objects, look up additional reference information, and send me random feedback. You can also find this podcast on Facebook and on Twitter. The audio was recorded and edited by George Bendo. The music is Immersion by Sasha Endy at www.sasha-endy.de, and the sound effects are from the Free Sounds Project at www.freesounds.org. Thanks for listening.